Welcome to this lesson on linear span. Today, we are going to explore one of the most foundational and beautiful concepts in linear algebra. We will learn how a small set of basic building blocks can be used to construct entire mathematical spaces. Let us dive in and see how this works. Before we look at any math, let us build our intuition. Imagine you are an artist and you only have exactly two tubes of paint, pure red and pure blue. By mixing different amounts of these two colors, you can create a huge variety of new colors like purple, pink, or dark navy. The complete collection of every single color you can possibly mix using only those two tubes is called the span of your paint set. In linear algebra, we do the exact same thing. But instead of mixing paint, we mix mathematical objects called vectors. Now that we understand the paint analogy, let us look at the mathematical objects we are mixing. A vector is simply an arrow pointing in a specific direction with a specific length. To mix these vectors, we use a process called a linear combination. This means we take a set of vectors, multiply each one by a plain number, called a scalar, to stretch or shrink it, and then add them all together tip to tail. Every time you choose different scalars, you create a brand new vector. This scaling and adding is the core engine of linear algebra. This brings us to the formal definition. The linear span of a set of vectors is defined as the set of all possible linear combinations of those vectors. Let me explain that in simpler, everyday words. If you treat your starting vectors as basic building blocks, the span is the complete list of every single destination you can possibly reach by walking along those blocks. It is the infinite mathematical space generated by applying every possible scalar multiplier to your starting vectors and summing the results. It is the absolute limit of what you can build. Now that we know what a span is conceptually, let us look at its mathematical formula. This formula literally says that the span, denoted by S, is the collection of all possible results you get when you multiply each vector v by some scalar number c and add them up. The symbols v1 through vk represent our starting set of vectors. The symbols c1 through ck represent scalars, which are just ordinary real numbers chosen from the set of all real numbers, denoted by r. As you change the values of the scalars, you sweep out a line, a flat plane, or even higher dimensional spaces. Let us visualize this formula in action. Here, we are looking at a three-dimensional space. We start with just two arrows, labeled as V1 and V2, pointing in different directions from the origin. By stretching, shrinking, and adding these two arrows in every possible way, we can reach any point on the flat shaded surface shown in the image. This flat surface is a two-dimensional plane, and it represents the complete linear span of those two starting vectors. Notice that we cannot reach any point above or below this flat plane using only these two vectors. Now that we have seen a two-dimensional span, let us scale things back and find the linear span of a single non-zero vector. We want to know what geometric shape is formed by all possible linear combinations of just one vector. Since we only have one vector, a linear combination simply means multiplying this single vector by any real number scalar, which we will call c. The new vector y is created by multiplying our starting vector v by the scalar number c. Let us see what happens as we change the value of c in a concrete example. Let us find the linear span of a specific vector in a standard two-dimensional space. We are given the vector v with components 2 and 3. The numbers 2 and 3 are the horizontal and vertical components, telling us how far it points left to right and up to down. We substitute our specific vector into the equation we just learned. We are asking what happens when we multiply this specific vector by any arbitrary scalar c. Why do we do this? Because evaluating this multiplication will reveal the geometric shape of the entire span. Continuing our calculation, we distribute the scalar c to both components of the vector. This final expression represents every possible vector in the span. If we choose c equals 1, we get our original vector. If we choose c equals 2, we get a vector twice as long. If we choose c equals -1, we get a vector pointing in the exact opposite direction. Because c can be any number, this process creates an infinite number of vectors that all lie on a single infinitely long straight line passing through the origin. Physically, a single vector can only ever span a line. We have seen how to generate a span. But what if we are given a target vector and we want to know if it lives inside a specific span? To find out if a vector W is in the span of V1 and V2, we must check if there is some combination of scalars that makes this equation true. We set our linear combination equal to the target vector W. The vectors are known, but the scalars C1 and C2 are unknown. If we can solve for these scalars, the vector is in the span. If the equation has no solution, it is outside the span. Let us see this with a concrete example. Suppose we have two starting vectors, v1 equals 1, 0 and v2 equals 0, 1. We want to determine if a third vector w, which is 4, 5, is located inside their linear span. In other words, can we build the vector w using only v1 and v2? We start by writing out the linear combination equation using our specific vectors. We are asking how much of the first vector plus how much of the second vector will exactly equal our target vector. Continuing with our equation, we multiply the scalars into the vectors. The first vector only affects the top number, giving us c1 and 0. The second vector only affects the bottom number, giving us 0 and c2. Next, we add the two vectors on the left side together to get a single vector. This simplifies our equation beautifully. We now have a single vector on the left and our target vector on the right. We are now ready to compare the two sides to find our unknown scalars. By comparing the top and bottom components of the left side to the right side, we can clearly see the solution. We have found our scalars. C1 equals 4 and C2 equals 5. Because we were able to find real numbers that make the equation work, we have proven that the vector W is indeed in the span. Physically, this means if you take 4 steps in the direction of the first vector and 5 steps in the direction of the second vector, you will land exactly on the target vector. Now that we have calculated spans, let us understand why this matters in the real world. Understanding the linear span is incredibly important because it tells us the absolute limits of a system. Think about a robotic arm in a factory that has 3 motors, where each motor provides movement in a specific direction. The linear span of those 3 motor vectors dictates every single point in space that the robotic hand can possibly reach. If a tool is located outside of this span, the robot will never be able to reach it. It is the mathematical way of asking, what is the full potential of the tools I currently have? We have covered a lot of ground today, so let us review the key takeaways. First, we learned that a linear combination is the process of scaling and adding vectors together. Second, the linear span is simply the complete collection of all those possible combinations. We saw that a single vector spans a straight line, while 2 vectors can span a flat plane. Finally, we learned that the span represents the entire mathematical space those starting vectors can build. You now understand the fundamental boundaries of vector spaces. Great job!